Hello students. So welcome back to our sessions. So today we will be starting a new chapter that is items from your grade 12 second part of your syllabus. Right. So this is a very important chapter in the modern physics, which includes about 12 marks, 12 to 15 marks in your board examination. Right. So let's straight away go to the chapter. We have already talked about dual nature of matter. So we have already understood what is interference, what is diffraction, how the wave theory is able to explain the interference and diffraction, right? And we have also seen how matter and radiation have dual nature, that is the particle nature and the wave nature, right? So in this particular session, we will be going through several atomic models, which led to the foundation of proper understanding of what atoms are, what are they consisting of. So all these things will be having a basic idea. Although you have studied about certain models in your lower grades, in chemistry also, so you studied about atom model, Dalton's atomic model, like you have studied about Thomson's atomic model. All these things you have already studied, right? We will have a brief overview of those models as well. Then we will quickly move on to the Rutherford's model, which is very important from our board exam point of view, and also the alpha particle scattering experiment, how the Rutherford's model failed, and what led to Bohr's model, what are the major postulates of Bohr's model, and what were the benefits, right? What did Bohr's model offer? So we'll go through all those points step by step, right? Okay, let's first try to understand about atoms. So initially, in the earlier stages, like in even in BC years, people had some notion of what atoms were. So we know if you start dividing any object, like if I have a table in front of me, if you keep on dividing this table until you reach to a very small particle where you can't divide it further. So that was called the atom, right? The indestructible particle of matter, right? So, so the indestructible particle of matter, that's what people called atom, or in Hindi, Parmanu, right? So when we divide matter into the tinier particles, ultimately we reach a stage where matter cannot be divided further, right? And also Democritus, there was another very interesting personality. He stated that the matter consisted of indivisible particles called atoms. Okay, and there is also empty space inside it, according to him. So atoms are indestructible, atoms are unchangeable, atoms are homogeneous. So all these were the ideas put forth by these people, right? Now comes the Dalton's atomic model. So again, you have studied about Dalton's atomic model. We will just go through quickly through the postulates, although this is not as important for your board point of view, right? So all matter is made up of tiny particles of atoms called atoms. Atoms are indivisible particles that cannot be created or destroyed, right? That is, no new atom is formed and no atom is destroyed. Another postulate states that the atoms of a given element are identical in mass and chemical properties. So if you're talking about the atoms of the same element, then they are supposed to have same mass, they're supposed to have identical chemical properties, right? If they are of different elements, definitely their mass will change, their chemical properties will change. That's what according to Dalton's postulate, right? The next postulate states that the atoms combine in a ratio of small whole number to form compounds. We have studied this in chemistry, and the relative number and a kind of atoms are constant in a given compound. Okay. Now comes the Thomson's atomic model. So an atom consists of positively charged sphere with electrons embedded in it. Like you can see the picture of this watermelon over here. So this Thomson's atomic model was compared to a watermelon, right? So in watermelon, there is a red part and there is a black part, which is the seeds. So the red part is the positive part of the atom, so which is actually the The positive part, the red part, and the black part, the negative part. Okay, so the positive charge is the red part, and negative charge or the electron is the black seeds, right? And although there were negative and there were positive charges inside the atom in this model, the atom as a whole was considered electrically neutral because the number of positive charges and number of negative charges are equal in magnitude, right? So this gave a brief but really good idea about the positive and negative charges inside, although the model was not good. Okay. So what were the limitations? The main limitation was it was not able to explain the stability, it failed to explain how the positive charges hold the negatively charged electron in an atom. It was not able to explain that, right? So again, Thomson's model failed to explain the scattering of alpha particle by tinfoils. So there was no experimental evidence as well, obviously, because at that time it was very difficult to find experimental proof of things, right? So, especially at the scale of atoms, which was really difficult, right? So, we will go through this alpha particle scattering experiment in a while. So, I'm not explaining that point here, okay? So, Rutherford's atomic model. From here, please make sure you are making proper note, and this is very important from the board point of view, right? So gold foil experiment, right? So what we had is we had a alpha particle source which emitted alpha particle, right? So alpha particle, what do you mean by alpha particle? Alpha particle is something which you have already seen many times in this throughout this year, right? So you know alpha particle is helium atom with two electrons lost. So basically helium has how many atoms? Two atoms, two electrons. Sorry, helium has two electrons. So if those two electrons are lost, what is remaining in helium? Helium nucleus, right? Helium nucleus. This is something what we call alpha particle. So this there is, let's say there is, we consider some source of alpha particle, right, emitted by some radioactive source. Okay, and this alpha particle emitted is collimated into a narrow beam. What do you mean by collimated into a narrow beam? It's made to move focused manner through a certain path, right? So it's made to move like a narrow beam focused in a certain path. And this collimation, this focusing is done by using something called, something like lead bricks. Lead bricks. Okay. So the beam was allowed to fall on a thin gold foil, and the scattered alpha particles were observed through a rotatable fluorescent screen and microscope. The scattered alpha particles on striking the screen produced a brief light flashes. Like you can see a ring-like shape over here, like this. So this is the fluorescent screen that we are talking. So once the alpha particle, the focused alpha particle, which are very narrow beam, reaches to this gold foil, some many majority of the alpha particle gets, move past the gold foil undeviated without having any deviation. But there are few alpha particles which are getting scattered at different angles, some even at 180 degree. But their number is very, very, very less. And how do we identify which alpha particle, I mean, how many alpha particle has gone by what angle, right? So the angle of scattering, how do we find that? Right? For that purpose, we have this screen, this circular screen placed over here, right? So what does it do? When the alpha particle, after getting scattered from this gold foil, they reach to this screen, and because of the properties of the material, what happens? They emit a brief flash of light, and by that we are identifying that the alpha particle has struck there, and that's how we determine the angle by which it has been scattered, right? Okay. Now, as you can see, there are this gives you a proper idea. So this is the source of the alpha particle emitting alpha particle in this direction. Alpha particle passes through the gold foil. You can see majority of alpha particles are getting past the gold foil without having any significant deflection, almost no deflection. Now, there are some alpha particles which are getting deflected at small angle of deflection. right? And very few alpha particles which are having some angle of reflection greater than 90 degree, means this greater than this much angle. And also there is very rarely you can find few alpha particles which are getting reflected by almost 180 degree. So what does that tell you? These are the observations. These are the observations from these experiments. Now you have to come out with some conclusions, right? So what are the conclusions here? Because this beam of alpha particle coming and passing through this gold foil, out of them, majority, if they are passing through the gold foil, then what happens? The only logic behind that is that there is nothing to stop them from passing straight, right? That means there is a lot of gap, lot of space inside the atoms, lot of space inside the atoms, which uh, because of which these alpha particles are getting undeviated while passing through the gold foil, right? So the first conclusion we can draw from this is that the majority of space in the nucleus is empty, right? Majority of the space inside the, not the nucleus, sorry, majority of the space inside atom. Suppose this is the atom. So majority of space is empty. That's why majority of the alpha particles are able to pass undeviated. Right. Now, why are some of them getting deviated? Because there is a small mass of the whole mass of the uh, atom is concentrated at the center. Let's say at this point. So the entire mass, almost entire mass of the atom is concentrated at the central point in a very small space. That is why alpha particles are passing without any obstruction. Now, if the mass was large enough, if the central mass was large enough, let's say, in that case, what happens if it was large enough like this? Then majority of the alpha particle won't be able to pass through. That means they will get deflected, they will get scattered because of the electrostatic force, because the alpha particle themselves, as I have told you, it is He2 plus. So they're positively charged. When they come closer to the nucleus, which are again, nucleus is also positively charged, they get deviated, they get deflected, right? So He2 plus or the alpha particle can easily pass through because there is nothing to obstruct them. And that means the mass inside the atom is concentrated in a very small space. So that is the reason. Okay. And almost all of the mass is concentrated in this very small space. Here you can see the observations. So on the y-axis, you can see the number of scattered particles detected by using that fluorescent screen. And you can see on the x-axis, we have the scattering angle, right? So scattering angle basically, you can see for 20, let's say, let's take an example. So the number of alpha particles which were detected, you know, less than 20 degree scattering angle is, close to 10 raised to 5, right? 10 raised to 5. But majority of the alpha particles, like 10 raised to 7, you can find very close to 0 degree angle. So majority of the alpha particles here are very close to the initial path. That means they are getting undeviated. If their scattering angle is almost equal to 0, then that means they are not getting deviated much. Also, you can see some values over here. Like most of the alpha particles pass straight through the gold foil, only about 0.1%, right? Which is very, very small. Only about 0.1% of incident alpha particles scatter by more than 1 degree, right? So you can imagine how small that number is, right? 1 in 8,000 alpha particles were deflected by more than 90 degree. Okay, and the predicted trajectory is shown in the curve, and the observed values denoted by dots. These are the observed values, as you can see. Okay, again, we will look at some of the terms regarding this alpha particle scattering experiment. First, let's look at a term called impact parameter. What do you mean by impact parameter? All right. So as you can see, let me share my screen again. Okay. So as you can see here that what do you mean by impact parameter? We were discussing about impact parameter, right? For example, an alpha particle is going along this path. An alpha particle is going along this path. Okay, along this path like this. Okay. Now, supposing nucleus is at this point, nucleus is at this point, and the alpha particle, because of the repulsion, small repulsive effect from the nucleus, this gets deflected slightly, let's say. So it gets deflected slightly like this. So this is the new path of the alpha particle. This is the new path of the alpha particle. Okay. Now, if you extend this, this is the initial direction of alpha particle. Now, if you extend this initial direction, the straight line, you extend this, you can see the perpendicular distance made by the initial direction of motion of the alpha particle with the nucleus. This perpendicular distance, this is called the impact parameter V. This is the impact parameter V. Okay, so what is impact parameter? It's a perpendicular distance from the initial velocity vector of the alpha particle to the center of the nucleus. Right. The trajectories of the alpha particle depends on the impact parameter, right? Smaller impact parameter means, what does that mean? Smaller impact parameter means that the particle is moving closer, right? The smaller impact parameter means if you extend this initial velocity vector, means the particle was supposed to go very close to the nucleus. This is the smaller, let's say B dash impact parameter. So in that case, what happens? Then in that case, the deflection will be larger. Deflection will, because it's closer to the nucleus, so the deflection will be larger, right? So as you can note down these. So smaller the impact parameter, collision result in larger scattering. For larger impact parameter, that means alpha particle is, somewhat farther away from the nucleus, and it goes nearly undeviated and has a small deflection. If it has a deflection at all, it will be really small because the impact parameter is large, meaning the alpha particle is moving farther away from the nucleus, right? So in the case of head-on collision, the impact parameter is minimum. The alpha particle rebounds, like it rebounds by 180 degree, right? So, and this happens very rarely because why? Because the whole mass is almost concentrated uh, at this point, which is at the center of the atom, and it's very small. It's in a very small region. So the chance of alpha particle hitting it exactly, undergoing a head-on collision and getting deflected back, it's less compared to it getting deviated or it passing straight without deviation, right? So you can see this is the relation you can remember for impact parameter. So where Z is the atomic number of the foil element, like in this case we had gold foil for the experiment. So B, the K value, K is a initial, Ke is the initial kinetic energy. K is a constant having value 1.77 MeV, mega electron volt. And the theta is the scattering angle, this theta in the cos theta here. Okay, so what are the conclusions made from Rutherford's atomic model? So the first conclusion is that majority of the space, most of the space in an atom is empty. And second, positive charge occupies a small space inside the atom, right? So most of the space is empty. That's why you can see majority of the alpha particles are getting uh, are passing without any deviation through these atoms, right? So positive charge occupies a small space inside the atom, right? And there is a positively charged center in the atom called the nucleus, and nearly all the mass of the atom resides in the nucleus. Okay, nearly all the mass, although there are some electron mass outside the nucleus, but compared to the mass of the nucleus and the neutrons, it's very less, right? So the size of the nucleus is very small compared to the size of the atom, right? And the electrons revolve around the nucleus in a circular path. Okay. Now, another term which is very important in this topic is the distance of closest approach. Okay. What do you mean by distance of closest approach? Here in this case, suppose consider an alpha particle projected from this point in this direction, and we have along this path we have kept an atom or a nucleus here. Okay, this is a nucleus with atomic number Ze, where the total positive charge is Z, where Z is the atomic number. So what happens? Here the alpha particle goes along this path. It will, once it reaches closer to the nucleus, as I have already told you, this alpha particle is He2 plus, so it's a positive charge. So once it approaches the nucleus, comes closer to it. So let's say at this point, its kinetic energy becomes zero. Why does its kinetic energy become zero? Because because of the Coulombic repulsion between the alpha particle and the nucleus, this alpha particle gradually slows down as it approaches the nucleus because of this repulsion in the opposite direction by the nucleus. So there will be a point when the velocity finally becomes zero. So this is the point where the velocity is zero or the kinetic energy value of the alpha particle is zero. So this point, the distance of this point from the nucleus is what we call the distance of closest approach, which we denote by R naught. Fine. So we have to calculate this value of R naught, right? And for that purpose, we will use the conservation of energy. Okay. So by conservation of energy, the total energy at this point, let's say this is point A, and this point is, let's say, point B. So total energy at point A should be equal to total energy at point B, right? Energy cannot be destroyed, right? So, so total energy at point A is the sum of the kinetic energy and potential energy, right? And this point A is very far from the nucleus. So we take this point A to be approximately at infinity, right? So we can say total energy is equal to kinetic energy initial at A plus potential energy at A. And total energy at B is equal to kinetic energy at B plus potential energy at B. So what is the kinetic energy at A? Kinetic energy at A is half m VA square, where VA is the velocity given to the alpha particle at point A. Plus, what is the potential energy? Potential energy is K Q1 Q2. Q1 is the charge of the alpha particle, which is okay, which is 2 times E 2 times E, and for the nucleus the charge is Z times E divided by distance square, that is infinity. So that means this whole term will become zero. This whole term will become zero because 1 by infinity is zero. So this is equal to kinetic energy at point B is zero because the particle finally stops there for a moment and then returns back. Plus the final potential energy at B, that is K, that is 1 by 4 pi epsilon naught Q1 Q2 by R, that is 1 by 4 pi epsilon naught 2 times E, the charge of alpha particle, into Z times E by the distance, that is R naught. Okay, so from this you can easily reach to the expression for R naught. So half m VA square is equal to 1 by 4 pi epsilon naught 2E into ZE divided by R naught. Okay, so this expression can be written as yes. So from this, I can write R naught is equal to, taking R naught to the other side. This becomes 4 times Z times E square, 4 times Z times E square by 4 pi M epsilon naught VA square, 4 pi M epsilon naught VA square. Okay, so we can reach to this expression here. This is the expression for the distance of closest approach. Okay, now you can see an example here. You can see an example over here. When an alpha particle of mass and moving with a velocity v bombards on a heavy nucleus of charge Ze, its distance of closest approach from the nucleus depends on ms. The options are 1 by m square, m, 1 by m, and 1 by root m. Okay, so as you can see here in this question, we have also previously did the same thing. So the in this case, the distance of closest approach is 2e ze upon 4 pi epsilon naught ke kinetic energy, or we have already did it here that r naught is inversely proportional to mass. So r naught is inversely proportional to mass. So the option C is the right answer. Okay, now let's move to another topic. We will understand what is spectra, what is hydrogen spectra, right? So when if you take some hydrogen gas and if you try to excite this hydrogen gas to a higher energy state by passing electric current through it, it will emit some radiation. And the key point to note here is if this radiation which is emitted from this hydrogen gas is made to pass through a prism, you will not observe the 7 colors like you do with normal light, normal white light. So what you observe is a spectrum which contains specific wavelength on a dark background. Okay, so this spectrum is called emission spectrum. Okay, and it's discrete, meaning it contains only a certain value. It's not continuous, right? It contains certain specific wavelength on the screen. So this discrete spectrum couldn't be explained by Rutherford's model. That was one of its failures. We will see more into the failures of Rutherford's model. So when an electron is accelerated, electromagnetic radiation is produced continuously according to electromagnetic theory, right? So whenever a charged particle is accelerated, so according to electromagnetic theory, it should be emitting radiation. And if that is true, these electrons which are revolving around nucleus are definitely accelerating because they are moving in a circular path, right? So when they are moving in a circular path, they are accelerating because their direction is changing continuously at every instant. So they are getting accelerated, and because they are getting accelerated by electromagnetic theory, they should be losing some energy, right? But the problem is if they lose some energy, they can move to a lower energy state. That means if an electron which is revolving, as you can see in this figure, if an electron which is revolving in this circular path, because of its constant acceleration, if it loses some energy, it will move to a lower energy orbit. That means it will move along this path. It will move along this circular path along this path, right? So the radius is different here. The radius is smaller here. So in that case, the problem is if it continues to move along the circular path, if it continues to get accelerated, if it continues to lose electromagnetic radiation in this form, what happens? It will keep on reducing its orbital radius, and basically it will spiral into the nucleus as you can see in the second figure, right? So the orbital radius will decrease and the electron should collapse into the nucleus eventually. So that was one of the failures of Rutherford's model because it was not able to explain the stability of an atom. It was not able to explain the stability. Right. Another important point is it was not able to explain the discrete wavelength in hydrogen spectrum. Same thing we saw in the saw 2 slides back, right? So according to classical electromagnetic theory, the wavelength or the frequency of electromagnetic waves emitted by revolving electron is equal to the frequency of revolution of the electron. Right. So as the revolving electron spiral inwards, their angular velocities and hence their frequency of revolution would change continuously. Therefore, the frequency of electromagnetic waves emitted must change continuously. So that means all possible frequencies are possible, all possible wavelengths are possible, but that is not what is observed. We are observing only a line spectrum, we are observing discrete spectrum. Only a certain specific wavelengths are obtained, as you can see in the left side of this slide. Okay, like this. So there is 656 nanometer wavelength here, 486 nanometer, 434 nanometer, 410 nanometer. These are all discrete, like it's not a continuous spectra, like everything is present there. But that is not what should be according to the classical electromagnetic theory, right? Okay. Now, after all these failures, Bohr came up with his own model that is, which tried to explain the disadvantages posed by the Rutherford's model. Okay. So in his model, Bohr postulated that the first postulate is an electron in an atom could revolve in certain stable orbits without the emission of the radiant energy. Okay, so there are, according to Bohr, the electron could not revolve in any possible orbits. Like that's what was possible according to the Bohr model. Electron could have had any possible radius and could revolve in any possible paths, but it has to be circular, that's all. But in here, in Bohr's first postulate, it says that the electron in an atom could revolve only in certain stable orbits, not all possible orbits. Right. Now, these particular orbits in which the electrons were able to revolve, in those orbits, they would not emit radiation. So that was a very crucial point of Bohr's postulate or Bohr's model of atom. So in these stable orbits, electron would not uh, emit radiation, right? So each atom has a definite certain stable states in which the electron can exist, and each possible state has a definite total energy, right? So there is a certain definite value of total energy for those orbits, and these stable orbits are called stationary orbits. They are called stationary orbits of the atom, stationary orbits. The necessary centripetal force for the orbital motion of the electron is provided by the electrostatic force of attraction between the nucleus and the electrons. Okay, so we know for any object to move in a circular path, it needs a centripetal force, just like centripetal force is what makes Earth revolve around Sun because of the gravitational force towards the center, right? Similarly, if you take a thread and if you have a stone tied at the end of the thread, you're able to rotate it, and this stone moves in a circular path because the tension in the string is acting as the centripetal force, which is making the stone remain in the circular path unless you leave the thread, right? So the centripetal force in this case is provided by the electrostatic force of attraction, because the electrostatic force of attraction is given by 1 by 4 pi epsilon naught Q1 Q2 by R square. Q1 is the charge of the electron, which is E, and ZE is the charge of the nucleus, where Z is the number of protons, and if there are Z number of protons, total charge of all the protons will be ZE divided by r square. This is the electrostatic force of attraction. This electrostatic force of attraction provides the centripetal force required for the electron to move in the circular path, where v is the velocity in the circular path and r is the radius of that circular path. Okay. Now, similarly, there is a second postulate in Bohr's model, that is in stationary orbits, the angular momentum of the orbiting electron is quantized. What does that mean? The angular momentum is quantized means it cannot have all possible values. You have studied about angular momentum in your work in 11th. So angular momentum is equal to mvr, right? mvr, where m is the mass, v is the velocity, r is the radius. So if for a electron rotating around the revolving around the nucleus, we has a certain value of angular momentum. But according to Bohr's second postulate, all possible values of angular momentum is not possible. The only possible values of angular momentum is integral multiple of h by 2 pi. Integral multiple of h by 2 pi. So it can be any multiple of h by 2 pi. H by 2 pi. Right. So other than this, angular momentum cannot have any other values. Right. So that is according to Bohr's second postulate. In this, h is the Planck's constant and L is the angular momentum definitely. Right. Okay. And n can have values 1, n can have values 1, 2, 3, etc. Right. N is equal to 1 corresponds to the ground state, right? N is equal to 2 corresponds to the first excited state, right? Similarly. So what is Bohr's third postulate? So energy of the atom has a definite value in a given stationary state. The electron can jump from one stationary orbit to the other, right? So if it jumps from an orbit of higher energy to an orbit of lower energy even, it emits a photon of energy E2 minus E1, right? So like in this case, you can see in this case, so the electron is jumping from a higher energy state, which is having energy E2, and it is jumping down to a lower energy state having energy E1. So if it has to move from a higher energy state to a lower energy state, definitely it has to lose some energy that it has in order to move to a lower energy state, because otherwise it can't occupy that lower energy state. So it has to lose that energy in some form, and the electron can emit a photon which corresponds to this energy difference. So the electron, while jumping from higher energy level to lower energy level, will emit a photon whose energy is equal to the energy difference between the E2 and E1 values. So E2 minus E1 is equal to h nu, where nu is the frequency of the emitted photon, right? So similarly, if it is already in a lower energy state, if it wants to go to a higher energy state, it can absorb a photon to increase its energy and hence move to a higher energy state. Okay. Now, again, this Bohr model of atom is only applicable to hydrogen-like atoms, right? So hydrogen-like atoms means the atoms or ion with one or single electron. Okay, so there should be only one single electron for this model to be applicable. Okay, so example, as you can see, helium plus, lithium 2 plus, beryllium 3 plus, boron 4 plus. These are all examples of hydrogen-like atoms. So Bohr model can be applied to any of these. So you have to be very careful, because in question, if they are asking, if they are giving any of these ions, you have to be familiar with them, right? So they are hydrogen-like ions. So definitely Bohr model will be applicable for them. So in Bohr's model of atom, we have seen how certain ions can also be understood in terms of Bohr's model of atom, like lithium 2 plus. Okay, so we have seen that lithium 2 plus, beryllium 3 plus, boron 4 plus, like that. All right. So now, in the case of hydrogen-like atoms, how do we find the radius of the nth orbit? So we will try to understand that next. Okay, so we know that angular momentum is quantized. That means it will only have certain specific values. That is integral multiple of h by 2 pi. Okay, and this should be equal to mvr. So from this, we can get an expression for the velocity, or we can get an expression for, yeah, if you take an expression for velocity over here, this will be nh by 2 pi mr. nh by 2 pi mr. Okay, so also we know that centripetal force is provided by, that is mv square by r. The centripetal force is provided by the electrostatic force of attraction between the electron and the nucleus. So that will be electrostatic force of attraction is 1 by 4 pi epsilon naught. E, the charge of electron, Ze, the charge of nucleus divided by r squared. From this I can cancel out r, and the value of r becomes r is equal to r is equal to Ze square by 4 pi epsilon naught m v square. Now, if you substitute for this value of v from this equation, let's call this equation 1. From this equation, if you substitute for v, the equation for r becomes Ze square by 4 pi epsilon naught m v square. So v square is nh by 2 pi mr whole square. So this expression becomes Ze square by 4 pi epsilon naught m n square h square by 4 pi square m square r square. So I can cancel out some of these terms over here. So this expression becomes 4 pi cancelled out, pi cancelled out, 4 cancelled out, one of the m's cancelled out. Then on the left hand side we had r. Okay, so again taking this to the numerator, Ze square times pi m r square, pi m r square divided by epsilon naught n square h square. So from this again r cancelled out. So the r value is equal to epsilon naught n square h square by pi z e square. So this is the value of r I'm getting from here. Okay, so this is the radius of the nth orbit. Fine. This is the radius of nth orbit. Radius of nth orbit. Now we had an expression for velocity where we can substitute this r and we can get the value of velocity as well. The velocity is equal to nh by 2 pi mr. Velocity of the nth or electron in the nth orbit is nh by 2 pi mr. 2 pi mr. So this becomes nh by 2 pi into m times r is epsilon naught n square h square by pi z e square. So pi cancelled out, z e square goes to the numerator. That is velocity of electron in nth orbit is equal to uh, z e square nh by 2m epsilon naught n square h square. So we can do some calculations over here. nh cancelled. So this is z e square by 2 epsilon naught m nh, 2 epsilon naught m nh. This is the value of electron, the velocity of electron in the nth orbit. Okay, so we have the radius of the electron in the nth orbit and velocity of the electron in the nth orbit. Okay, now you can see over here that if you take the radius of electron in the nth orbit, you can take everything else and n square by z separately. Okay, so you can see over here whatever I have written here. So in this expression, this can also be written as Rn is equal to epsilon naught h square by pi z e square. Sorry, I will take this z separately as well. Okay, pi e square multiplied by n square by z. Okay, n square by z. So this whole term over here, this whole term outside the bracket can be found out to be 0.53 Armstrong. So 0.53 n square by z square or z Armstrong. This is the value of electron in nth, the radius of the electron in nth orbit. Okay, so if you have the radius of the electron in the nth orbit, you can find the and we have also found out the velocity of electron in the nth orbit, right? And from that we can also find the time period of the electron in the nth orbit. Because if you know the velocity, it's easier to find the time period because If the electron is moving in a circular path orbiting around the nucleus, clearly the orbit having radius Rn, nth orbit radius, the velocity is also given, velocity in the nth orbit. So in that case, the time period is equal to distance by speed, right? So distance is 2 pi Rn, the perimeter distance covered in one complete cycle, divided by the speed, which is velocity in nth orbit. So that will give you the time period of electron in nth orbit. So time period in this case is, sorry, the radius is, yes, the radius is, what is the value of radius? Epsilon naught n square h square by pi z e square. So 2 pi into epsilon naught n square h square by 2 pi e square, right? 2 pi, sorry, pi z e square. Okay, let me replace that here. So we have pi z e square, right? So this divided by the velocity of electron in nth orbit, z e square by 2 epsilon naught m n h, right? So pi cancelled out. Okay, so this becomes 2 epsilon naught n square, 2 epsilon naught n square h square. Okay, epsilon naught n square h square. So divided by z e square into 2 epsilon naught m n h divided by z e square. Okay, so again the time period becomes 2 epsilon naught n square 2 epsilon naught square into n cube h cube into n cube into h cube into n divided by z e square whole square. Z e square whole square. Okay, this is the equation for time period. Okay, okay, all right. Now, the if the time period is clear, then we can easily find the frequency as well, because frequency is given by 1 upon time period. So frequency is equal to 1 upon time period. This is 1 upon time period, the reciprocal of that, that is z square e raised to 4 divided by 4 epsilon naught square n cube h cube times, this is the value of the frequency of the electron, frequency of electron in the nth orbit, right? So similarly, you can find the value of kinetic energy of electron in the nth orbit, because kinetic energy of electron can be found out and potential energy of the electron can be found out, right? So how do you find the kinetic energy? Because we have the radius and we have the velocity, right? Velocity of electron in the nth orbit. So from the expression for velocity, we can reach to the expression for kinetic energy as well. Kinetic energy is equal to half mv square, or this is half into mass of electron times velocity square. That is, in the nth orbit, the velocity will be z e square by 2 epsilon naught m n h, this whole square. So this is m z square e raised to 4 by 4 epsilon naught m n h, 4 epsilon naught m n h. Okay, this is the expression for kinetic energy. And if you, sorry, there is a 2 here as well. So this will be 8 epsilon naught mnh, 8 epsilon naught mnh. Similarly, if you talk about potential energy of the electron in the nth orbit is 1 by 4 pi epsilon naught q1 q2 by r, where r is the radius of the electron in the nth orbit, q1 is the charge of the electron, q2 is the charge of the nucleus, and the potential energy is 1 by 4 pi epsilon naught q1, charge of electron, which is negative. And while you calculate potential energy, you have to take it along with the sign. Okay. Now minus e into ze positive divided by r. What is the radius here? Epsilon naught n square h square by pi z e square. Epsilon naught n square h square by pi z e square. Okay. pi z e square. This goes to the numerator. So minus z e square into pi z e square divided by 4 pi epsilon naught into epsilon naught n square h square. So again you can see here. Okay, so again you can see over here. In this case, this will be pi cancelled out. Then we have, yes, so this becomes z square e raised to 4, uh, z square e raised to 4. Okay, okay. So z square e raised to 4 divided by epsilon naught square n square h square. And in this case, we had a 4 over here. We had a 4 over here. So this 4 remains here. This 4 epsilon naught square n square h square. Okay, epsilon naught square m square n square h square. Right. Okay, there is a small error that we made over here, that we forgot to write this m here. We forgot to write this, carry this m to the denominator while we were calculating the radius. So this will be pi z e square into m. This will be pi z e square into m. Sorry for that. And we have to take this m along here. So this expression becomes epsilon naught. If you put this m here as well, this m gets cancelled here. So this expression for velocity is this expression for velocity. Yes. Okay. This expression for velocity is without m to epsilon naught nh. Okay. So that is some correction you have to make here. And Vn, the velocity equation, does not have an m here. So this is m cancelled out here as well. So everywhere you have to make that correction actually. Okay, there is no m here. Okay. Okay. So we can find out the radius of the electron in the nth orbit. So we know angular momentum, all the angular momentums are not possible, right? So angular momentum is quantized, and the possible values of angular momentum, MVR, is equal to NH by 2 pi. That means only integral multiple of h by 2 pi is possible here. So from this, we can find an expression for the velocity, which is given by NH by 2 pi mr. NH by 2 pi mr. So similarly, we can find out an expression for the radius of the electron in the nth orbit. Radius of electron, radius can be found out, radius of electron in nth orbit, right? How do you find it? So we know the mv square by r, the centripetal force, is provided by the electrostatic force of attraction between the electron and the nucleus. That is 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, q1 q2 by r, q1 q2 by r square. Okay, so here this r, if you see, can be removed. One of the r can be cancelled. So this r becomes equal to 1 by 4 pi epsilon naught q1 q2. What is q1 q2? Charge of electron times the charge of nucleus divided by mv square. We are taking the mv square to the other side. So m into v square, right? So I will replace the v square with the expression for v square that I have over here. So this expression I will replace here. So this becomes 1 by 4 pi epsilon naught z e square by m into v square. So v is to nh by 2 pi mr. So v square will be n square h square by 4 pi square m square r square. Okay, so this one of the m cancelled out here. So this becomes 4 pi and 4 pi square cancelled out. So this finally becomes equal to, I'll write it here. So this is pi m r square times z e square by n square h square. This is the expression for r. So this r and this r can be cancelled out. So r becomes n square h square by pi m z e square. Okay, this is the expression for the radius of electron in the nth orbit. Very, very important. So we have the radius of electron in the nth orbit, n square h square by pi m z e square. So from this expression, I can substitute r into this and find out the value of velocity in the nth orbit. So velocity in the nth orbit can be written as velocity in the nth orbit is nh by 2 pi mr. And this r can be replaced 2 pi m. R is n square h square by pi m z e square. Okay, so this m cancelled out, pi cancelled out. So this becomes uh, z e square z e square nh by n square h square, and there is also a 2 here. So this nh cancelled out, so this expression becomes z e square by 2nh, z e square by 2nh. Let's quickly verify. So here we have velocity as nh by 2 pi mr. So we put this expression for radius of electron in nth orbit into this expression. So this becomes n square h square by pi m z e square, right? So this pi m and pi m cancelled out. So this z e square goes to the numerator. So z e square nh cancelled out here. So z e square by 2nh. Z e square by 2nh. This is the expression for velocity of the electron in the nth orbit. So if you have velocity, you can easily find out the value for kinetic energy of electron in nth orbit. Kinetic energy of the electron in nth orbit is kinetic energy is equal to half mv square. So this is equal to half into mass into velocity square. That is z square e raised to 4 divided by 4 n square h square. Okay, so we have m z square e raised to 4 by 8 n square h square as the value of kinetic energy. So similarly, I can find the expression for potential energy of the electron in the nth orbit. Potential energy is given by U is equal to half, 1 by 4 pi epsilon naught Q1 Q2 by R. Okay, so here 1 by 4 pi epsilon naught, what is Q1? Q1 is the charge of electron. While calculating potential energy, we have to take the sign of the charge minus E times ZE, charge of nucleus divided by R. What is R? R is n square h square by pi m z square. N square h square by pi m z e square. Pi m z e square, right? So we have z e square, z and e. Okay. So we have pi cancelled out here, pi cancelled out, this becomes minus z square e square into m. This goes to the numerator, z square e square into m, z square e raised to 4 into m, sorry, z square e raised to 4 into m divided by 4 epsilon naught n square h square. 4 epsilon naught n square h square. But there has to be an epsilon naught here as well. Did we forget any epsilon naught over here? Just let's quickly check it once. Yes. So we have velocity as nh by 2 pi mr. Okay, this expression becomes the radius is yes. Okay, there was an expression, there was an epsilon naught over here which we missed, so we can simply add it here. So epsilon naught n square h square, epsilon naught n square h square by pi m z square. Okay, that was a small error. So putting this here, so this is epsilon naught n square h square. Okay, So here again, this becomes, yes, epsilon naught n square h square. So actually we have to square it over here. Let me verify it. Yes. Okay, fine. So epsilon naught, we have added epsilon naught n square h square here. Then again, 2 pi m r epsilon naught n square h square. Yes. So there is an 2 epsilon naught nh. There is an epsilon naught here as well. So I'm putting that here. So 2 epsilon naught nh. Let me replace 2 epsilon naught nh here. 2 epsilon naught nh. Okay. So velocity is 2 epsilon naught nh. So this becomes 4 epsilon naught square n square h square. Okay. Let me once again write it here. So this is velocity in this denominator z square e square by 4 epsilon naught square n square h square. So m, so 8 epsilon naught square n square h square. So again r is epsilon naught n square h square. So epsilon naught into epsilon naught in this equation becomes 4 epsilon naught square n square h square. Now it's fine. So kinetic energy is this value, potential energy is this. So we can find the total energy as well. Total energy in this case, total energy is equal to kinetic energy plus potential energy. This is mz square e raised to 4 by 8 epsilon naught square n square h square minus z plus minus actually minus z square e raised to 4 m by 4 epsilon naught square n square h square. So multiplying the 2 over here to make the denominator same. So this becomes minus z square minus m z square e raised to 4 by 8 epsilon naught square n square h square. This is the expression for total energy. Okay, total energy. So total energy you can see is equal to, if you have kinetic energy, if you multiply, if you put a negative sign over kinetic energy, you will get the total energy. So kinetic energy with a negative sign will give you total energy. Okay. Or in the case of, you compare it with potential energy, if you multiply 2, like total energy multiplied with a 2 will give you potential energy. So you can remember these relations, right, between total energy and kinetic energy, and total energy and potential energy, right? Okay, so let's quickly go back to our slides. So we have seen all these expressions. Now we saw total energy is given by this value. And here in this case, there are a lot of terms in this total energy which are constants and which are having known values. Like in this expression for total energy, the mass is the mass of the electron. Z is the atomic number. If you're taking hydrogen atom, again, it will have a certain value. E is a constant which has a known value. Epsilon naught has a known value. H has a known value. So what is not having a known value here? I mean, what is a variable here is simply if you take minus m e raised to 4 by 8 epsilon naught square x square as separate and z square by n square as separate. If you solve it, you will get this value as 13.6 electron volt in electron volt, right? So this is why I can write it minus 13.6 z square by n square electron volt. So this will become the total energy, right? So that is why I'm writing it here like this. Okay, the total energy is minus 13.6 z square by n square electron volt. Okay, we have already seen this relation. Total energy is equal to negative kinetic energy is equal to potential energy by 2. Okay, so, and one more point which is very important here. Since the total energy of the system is negative, the system is a bound system, which means the energy must be provided to the system to separate out the particles. So whenever you see negative value in the energy, that means it's a bound system, right? So bound system. So total energy is minus 13.65 n square. From this, we can find the energy for the ground state, which is n is equal to 1. The ground state energy will be minus 13.6 electron volt. For the first excited state, n is equal to 2. The energy will be minus 3.4 electron volt. For the second excited state, the energy will be minus 1.5 electron volt. Okay. So these are the energies corresponding to different energy states, different orbits. When an electron jumps from higher energy state to lower energy state, the radiations are emitted, and the energy of these emitted radiation is equal to the energy difference of these two states, right? So energy initial, like if an electron jumps from this point, this level to this level, the photon emitted will have energy equal to the energy difference between those two states, right? Like we have seen in the Bohr's third postulate, right? E initial minus E final. This happens when we are jumping from a higher orbit to a lower orbit. The emitted photon will have energy equal to h nu, which is also equal to hc by lambda. Okay. So we are able to see only those photons or those wavelengths in the emission spectra, only those wavelengths which are corresponding to this energy differences. Okay, otherwise the wavelengths are not visible to us. Okay, so yes, so we will stop it here, this session. We will continue with the remaining topic in the next class. Please revise these topics, make proper note of these things, and do practice the derivations which we have discussed from this topic, especially the radius of electron in the nth orbit, velocity of the electron in the nth orbit, similarly, the total energy, kinetic energy, potential energy of electron in the nth orbit. Also, the postulates of Bohr, what are the conclusions and observations of alpha particle scattering experiment? What are the drawbacks of Rutherford's atomic model? Please go through all of these things, make proper notes, and yes, if there is any doubt, let's go through the class once again. Okay, thank you so much.